This video will be about a few mechanisms for ring changes. So we're going to start out with a familiar mechanism in terms of an alcohol and an acid. So what we know happens with an alcohol and an acid is we can protonate that alcohol. So that's the first thing I'm going to write down. And then H and H. Then I'm going to consider the product. So the product has 5 carbons. I do have 5 carbons here. But wow, the first thing that I thought would happen was maybe I could just lose a water. But no, this one is primary. And so instead I could imagine a hydride shift, and that will push out water. And so that could lead to, let's see, a carbocation at this position. And then I could maybe remove a proton with HSO4. And that would give me this product. Turns out that that double bonded 4-membered ring is a minor product because 4-membered rings are not very stable. Well, what if I do something slightly different and I say this carbocation, maybe instead HSO4 removed this proton, and so then I'd be left with this double bond. But again, yeah, and of course there are plus waters here, so it could have been water that did this, or H2O. This is very minor because that double bond within a 4-membered ring is very difficult to form and not very stable. So let's try another route. I could imagine that like a hydride shift happened, I could have an alkyl shift to push that water over. And so that would form a brand new carbocation. Let's see, 1, 2, 3, 4, 5. So 5-membered ring is what that would do. And then 1, 2, 3, 4, 5. From carbon 4, I'm taking electrons right there as I move them over. So carbon 4 should be left as a plus charge. And so then I can use maybe any water that was just lost, plus H2O, and it can remove a proton. We'll swing in to meet the requirements of a carbocation, which needs to be satisfied, and so our product would be this double bond. It turns out this is the major product because 5-membered rings are more stable than 4 or 3. Okay, so now let's consider a slightly different type of mechanism. This was a ring expansion. And so now what we're going to do is a ring contraction. So if I take this 7-membered ring and it's got a double bond and it's got this, and I put this in acid, so sorry, H2SO4. If you remember, I said that water coming on and off with acid was an equilibrium process, and so this is putting that H plus back on. And so what we should get, it turns out, is this product. And I'm going to show you the mechanism for getting there. So a 6-membered ring instead of 7. So that first step puts proton on to the double bond. And that leads to a carbocation right here. And you'd think you'd be done there, right? I'm going to number this. 1, 2, 3, 4, 5, 6, 7. But what happens, because we already said 5-membered rings were more stable than smaller, 6-membered rings are also favored, and they're even favored over 7-membered rings. So what we can have is this ring contraction can occur. So I'm taking the electrons from carbon 5 and 6 bond and making carbon 6 bond to number 1 where there's a carbocation. So the result of that is a 6-membered ring, and at carbon 1 I have something, and at carbon 1 I also have something, and I'm going to draw in let's see, carbon 1, 2, 3. I recommend you do this because it helps you keep track of what's happening. We said that the bond between 6 and 7 shifted over to carbon 1. So I should have a bond between 1 and 6. There's my bond between 1 and 6. And that left a carbocation out here at carbon 7. Carbon 7. And so now what can happen, let's consider that there's H's on those two methyl groups. The HSO4 anion, maybe? Did I heat this up? Takes that, the electrons swing in, and that leaves me with the product that I wondered how I got there. So it makes a double bond on there. If you want, I can draw that the other way, this direction. It doesn't matter. So that shows an example of a ring contraction, and before I had ring expansion. So sometimes when you're asked to do a mechanism, it doesn't mean it's the major product. So I don't know if this was major or minor. It just said, find this. How do I get there? And so we found a ring contraction can work.